Imagine a moon looming larger on the horizon than in the vastness of the night sky. Visualize a pencil bent as it touches the water, defying its own straight form. Now picture a chessboard where two identical tiles appear as if they're bathed in different shades, all because of a lurking cylinder. Well, welcome to the world of optical illusions, where what you see isn't always what you get. The moon illusion is an intriguing one. It's been known for thousands of years, but the mechanisms behind it are still debated to this day. Essentially, the illusion here is that when the moon, especially a full moon, is first rising up into the night sky, hovering just over the horizon, it appears to be abnormally large, especially when compared to the moon high up in the night sky. This is a well-documented phenomenon, and one you've probably noticed yourself even if you didn't realize it. And it's even weirder that for many people, the illusion often goes away if you bend over and look at the moon between your legs. Really? Since ancient times, it was believed to be a result of some form of atmospheric refraction, as the light reflected off the moon has to travel through more atmosphere to reach you through the horizon than it does coming down directly over your head, perhaps stretching the light a bit and making it appear larger as a result. Ptolemy, for example, was a fan of this theory, writing about it in the 2nd century. However, this explanation does not hold up under scrutiny. Atmospheric refraction would mean that the air is literally changing the path of the light. If this were true, it would be measurable in some way. However, a few simple experiments can show that the moon doesn't actually change size and that the whole thing is all in your head. An easy way to test this yourself is to take a piece of paper, roll it up into a tube, and hold it up to the moon like a telescope, and then just adjust the shape of that tube until it perfectly fits the moon inside of it. Tape it then so that it keeps that exact same shape, and then wait a few hours for the moon to rise high up into the night sky. Then take a look at the moon again through the paper tube, and you'll see that it fits perfectly in the circle. Its size hasn't changed whatsoever. This had become the consensus by the 1700s, but we still haven't reached an agreement on what causes it. One explanation is called the apparent distance hypothesis, which claims that the moon on the horizon appears to be larger because our brain perceives it as being further away. It perceives this distance because of the moon's position on the horizon, which we consciously know is a great distance from us. The idea goes that our brain knows that as things get further away from us, they tend to get smaller in our vision, making the moon seem oddly large in comparison since it doesn't seem to shrink at the horizon. Then, when it reaches its height in the night sky, it no longer has the horizon nearby to fool our brain, and we see it at its normal size. A similar idea is the relative size hypothesis, claiming that the moon appears larger on the horizon because our brain has an easier time grasping the size of an object when it's surrounded by others, such as buildings or mountains that are usually present. Then, when it's high up in the sky, the only thing it's surrounded by is the expanse of empty space, giving our brain a very different impression. At the end of the day, we don't really have a final answer. A 2013 book called The Moon Illusion featured 19 chapters written by different authors offering various explanations and came to the conclusion that not a single hypothesis could emerge victorious. The checker shadow illusion is certainly one of the most mind-bending optical illusions ever created. It was published in 1995 by Edward Adelson, professor of vision science at MIT. It's quite simple. It's a checkerboard with dark and light squares featuring a cylinder that casts a shadow over the board's center. Adelson marked two squares to pay attention to, A and B. And to anyone looking at the checkerboard, even those who already know what's going on, it seems that A and B are clearly different colors. A is a lot darker. But then if you use a color matching tool, you'll find that they are actually identical colors. So what's going on here? Well, unlike the moon illusion, we have a pretty good explanation for this one. It turns out this illusion takes advantage of the way our brains process visual information. When we look at something, there's several things going on inside our head as our brain breaks down the light received by the eyes. Part of this is the need to understand brightness, but our brain can't simply rely on the basic idea that more light equals a brighter shade. After all, a black object in the sun reflects more overall light than a white object in a dimly lit room, yet our eyes are still able to tell that one is brighter and one is darker. That's because alongside the total amount of light reaching the eyes, the visual system also factors in context using contrasts with nearby objects. Contrast here is incredibly important. You see, this illusion takes advantage of this mental shortcut and reliance on contrast. In the picture, the light square in the shadow is conveniently surrounded by darker squares, making it appear extra bright. Meanwhile, the dark square in the light is surrounded by brighter squares, making it appear extra dark. All of this together means that even though the squares are identical shades, our brain struggles to see them as such. And the checker shadow illusion isn't the only contrast illusion out there. A similar one is the corn sweet illusion, which also takes advantage of the way our brain uses edges to perceive objects and their shades. It appears that the left half of the corn sweet illusion is brighter than the right, but cover up the middle where the sides meet, and you'll actually see that they are identical. And finally, there's the chub illusion, where the center circles of each half appear to be different shades, but as you've grown to expect with these types of illusions, they are actually identical. A highly recognizable object and a perfectly straight line, pencils are a great tool to showcase illusions. First up is the broken pencil. Everyone's noticed that when a pencil, or a straw for instance, sits at an angle in a cup of water, it appears that the pencil is broken, offset, as it enters the liquid. Now, this isn't so much an illusion as more a lesson in the way light works. It's commonly taught that the speed of light is constant, coming in at 299,792,458 meters per second. But this isn't actually the full story. The full sentence is that the speed of light is constant in a vacuum. As light enters and travels through different mediums, its speed can change. In this case, light travels faster through air than it does through water. As it enters water, it slows down, and thus the path of the light bends or refracts. It doesn't change dramatically, but it's definitely noticeable, and this is why the part of the pencil in the air and the pencil in the water seem to be in slightly different places. But a pencil's behavior is a bit harder to explain in another situation. A common trick to show your classmates in school: all you have to do is hold the pencil at one end and wiggle it up and down at a steady pace. It makes it appear as if the solid wooden object is suddenly made of bendy rubber. The reasoning here, as with most illusions, is thanks to your visual system. When you look at the world around you, your brain tries very hard to perceive it as stable and consistent. However, this perception relies heavily on the brain's ability to interpret sensory information quickly and efficiently. In the case of the rubber pencil illusion, the brain is tricked into perceiving the pencil as flexible due to a combination of factors. First of all is the pencil's speed. Moving quickly means that our brains actually have a tough time keeping up with it. Estimates vary, but the general rule is that our eyes and brain can only process around 60 frames per second. This means that for many points in the pencil's path, our brain doesn't actually see it, and instead it fills in the gaps. And our brain is seriously good at filling in gaps. It loves solid objects and continuous motion, so instead of showing us a choppy image of a pencil jumping from place to place, it connects the dots with a bit of motion blur, and we end up with what appears to be a bending pencil. Interestingly, there are many species which can see more frames per second than humans, such as peregrine falcons, which, according to some research, can see as many as 130 frames per second, while some houseflies can see upward of 200. To these creatures, movies on a television screen might appear like a series of static images, and the bendy pencil trick certainly wouldn't work on them. Another way our brain fills in the gaps can be taken advantage of with illusions of incomplete shapes. This is the Ksar Triangle, and at first glance, aside from the circles missing a pie slice and the triangular corners, it seems there is a large, white, equilateral triangle standing out in the center of the picture. However, as real as it seems, the edges of this triangle don't exist at all. Your brain is creating the entire thing on its own. In psychology, this aspect of our vision is often referred to by the saying, the whole is greater than the sum of its parts. Our brain doesn't just add up the parts in our vision and create a picture, often it adds more on top. It's almost as if 1 + 1 = 3. There are several other examples of this, including basically every shape, and our brain falls for it every time because its pattern-creating instinct is to create shapes wherever possible. The other thing that's odd about the Ksar illusion is that the false white triangle also appears brighter than the rest of the image. This is another tactic our brain is using to add non-existent boundaries to help us perceive a real shape. The technical term for all of this stuff is the principle of closure, which states that our brains like to group nearby objects together as a single item wherever possible. However, you don't just see the effects of this in carefully constructed illusions. Many company logos take advantage of this as well, such as the USA Network logo. There isn't an actual S in the center, just the implication of one using the edges of the other letters, and your brain does the rest. The Hermann grid illusion is a strange one. As your eyes scan across the black squares, in the edges of your vision you'll notice small grey or black dots appearing in the intersections between the squares. However, when you try to look directly at one, it disappears entirely. This peculiar scene was first reported by Ludemar Hermann in 1870, and a similar one was created in 1994 called the scintillating grid illusion. This other one is different because white circles have been placed in the verticals, further enhancing the effect and causing some of them to appear as if they are blinking. Both of these are best explained through a neural process called lateral inhibition. Now, we're not going to get too into the details here as it's highly complicated, but we'll give you a basic rundown. Lateral inhibition allows us to see the world more clearly by having our cells in our eyes work together. When light reaches the cells, they don't just communicate that backward toward the brain, they also communicate with each other. When one cell detects light from a certain angle, it not only informs the brain that it saw this, but it also tells the other cells around it to quiet down, increasing contrast and making the image sharper. This helps our brain perceive edges of objects, light and dark areas, and more. In the case of the Hermann grid illusion, some cells are highly stimulated by the intersections of white lines as they are bright by contrast. As a result, they inhibit the activity of nearby cells, and due to the shapes in the picture, this inhibition takes place at the other intersections, making them appear darker, since even though your cells are seeing the white light there, they're not telling anyone else about it. However, lateral inhibition does not explain everything here. For example, if you make the lines in the grid a bit wavy instead of straight, both the Hermann illusion and the scintillating grid illusion fail to appear. Also, it doesn't fully explain how changing the size and length of the black bars maintains the illusion. Overall, it's an odd insight into the complexities of our vision, and really just puts into perspective just how much is going on inside our heads that we're entirely unaware of.